So after this gap, I am back again, and let's start now with classical mechanics. And this is chapter 1. It's about the algebra and calculus of vectors. And the first section is about vectors and vector quantities. I have written the first line as it appears in the text because there is something I noticed about this first line which will be important later on. Most physical quantities can be classified as being scalar quantities or vector quantities, which actually you already know. You in fact also know what a scalar quantity is and what a vector quantity is. A scalar quantity needs only a number for its complete specification, besides the unit of course, but to completely specify a vector quantity you need a number which is its magnitude as well as a direction, and there is a unit as well. But you concentrate on this first word, most. Most quantities are either physical quantities, are either scalar quantities or vector quantities, but not all. Some of them are neither scalar quantities nor vector quantities. We will see later on what those quantities are. Now let's see some examples of scalar quantities, and then we will see what the author has written in the text for vector quantities, what definition he has written. So the first example of a scalar quantity the author has chosen is the temperature in a room, and it's a scalar quantity because its value is a scalar. That means you just have to specify one number along with a unit to for its complete specification. There is no need for saying that temperature is this much and it's in this direction. That does not really mean anything. You just need the number and the unit, and that will specify it completely. And that number in our present context is a real number. It may be negative, temperature may be negative, but it's a real number. Besides temperature, these are also examples of scalar quantities. The volume of a can, the density of iron, the pressure of air in a tire, these are all examples of scalar quantities because each one of them needs only a number and a unit for its complete specification in a given situation. And next we are going to see the definition of a vector quantity. And next we have definition 1.1 of a vector quantity. You are actually already familiar with it, but still let's see what the author has written. There are some things which you may find a little striking. If a quantity Q, he has given it a name, has a magnitude and a direction associated with it, then Q is said to be a vector quantity, but that's not all. There is something else which now I am going to write. Okay, so here is the extra part which is not exactly the definition itself, but it has been made a part of the definition because it makes the original definition more clear. Let's see what it says. Here, magnitude, that magnitude means a positive real number. That is one thing. And direction is specified relative to some underlying frame of reference that we regard as fixed. So there is something called a frame of reference which we regard as given. It's there in the background and it's fixed, and with respect to that frame of reference we say what the direction of a vector quantity is. And there you see this star here because we are going to talk about frame of reference later on. Okay, more about this, what exactly a frame of reference is. We will discuss about it. For now, you just know that there is something with respect to which we give the direction of a vector quantity. But let us also see this word positive real number. The magnitude of a vector quantity is a positive real number. Does it not look like something has gone wrong with this definition? Can the magnitude of a vector quantity not be 0? Yes, it can be actually. But then why is the author saying that it is a positive real number? Well, the 0 vector, I am getting ahead of myself because I just now said the 0 vector. Note that this is the definition of a vector quantity, not a vector. There is a difference. That difference will become clear when we next define vectors separately. But just for the sake of making this situation more clear, you think of the 0 vector. The 0 vector is like a point in space which has a magnitude associated with it which is 0, but there is no direction. However, here we are talking about quantities having direction, and they are not going to be given or represented by the 0 vectors, they will be represented by non-zero vectors. When we ultimately define vectors, then they will all be non-zero vectors, and non-zero vectors have magnitudes which are positive real numbers. That is why the author has used positive here. Alright, now what are some examples of vector quantities? This is an example of a vector quantity. Displacement. The displacement of a particle is an example of a vector quantity. You consider two locations in space, say A and B, or for the sake of simplicity, suppose A and B are these two locations in this plane, the plane of the board, and a particle moves from A to B along two paths, say. One of them is this one which crosses itself and then eventually reaches B. Another one has these kind of straight parts which are line segments, straight line segments, and the other path is like this. Now for this motion of the particle starting at A and ending at B, the displacement is a vector quantity, and it is this one. So the displacement only takes into account the point where the particle started its journey and where it's ending its journey. It does not take into account the actual path that it followed to reach B from A. And this displacement vector has magnitude which is equal to the distance, the straight line distance between A and B, which is just the length of the straight line segment AB, and the direction is the direction of B relative to A. That means the direction going from A to B, this direction. So it becomes a vector quantity because you need to say two things, right? You need to say two things to completely specify the displacement of a particle. Simply saying that it's, the particle got displaced by say 1 meter is not enough. The particle can get displaced by 1 meter starting at A like this or like this, like this. So we don't really get to know the location of B, where it will ultimately be after having that displacement. We need to specify the direction also. Direction alone is also not enough. If you say that the particle got displaced in this direction, by how much? Is the displacement this much or this much? Or is it really large or extremely small? Or is there no displacement at all? So that's why two things are needed to completely specify this quantity, and that is why it is a vector quantity. Another example of a vector quantity is the force applied to a body by a rope. Say you have a very big stone and there is some kind of something is there, say a hook or something where you can tie a rope and then you can pull. Looking at this stick figure, you have probably guessed how well I draw. Okay, I cannot really draw very well. Of course, because you cannot push using a rope, so it will be a pull. The text doesn't say anything, but it's understood. So there is some object and you are pulling it using a rope. Alright. So you are applying some force. That force is a vector quantity. what is the magnitude of that force? Is that the length of this rope? No. That is something. Okay, that is the strength of the force that you are applying. You can either pull the rock with less effort if it is not really heavy and make it move, or you may have to really pull with a lot of effort if it is really heavy to make it move. But in either case, you are applying a force and its strength is the magnitude and its direction is towards the pull. It's the direction of the pull. So simply saying that I am pulling with this much strength is not enough. In what direction are you pulling? Also, the direction alone is not enough. You are just saying that I am say pulling it horizontally in this direction. How much effort are you putting into the pull? With what is the strength of the pull? So both these things have to be specified in order to completely specify the force. That is why force is a vector quantity. Some other examples are also given by the author of vector quantities. For example, the velocity of a body which is moving, or say it's not also moving, it's fixed with, it's standing still with respect to some reference frame, but still it's a vector quantity. The value of electric or magnetic field in a given place where there is a source of this field. So this, you see, you may think that value means scalar, but there is a direction involved also. Okay, so these are some examples of vector quantities. And now we are going to define vectors. We have seen what vector quantities are. Now we are going to define vectors. Remember, keep this in mind that in order to know the value of a scalar quantity or a vector quantity, you need to conduct an experiment where you will use some equipment to measure it. And because it's about measurement, you will make error. All those things are there. Okay, so there is a physical act involved in knowing the value of a quantity, a physical quantity. That is why they are called physical quantities. But now what we are going to define is a mathematical quantity known as a vector. So having seen those examples of vector quantities, the author next writes, in order to manipulate such quantities without regard to their physical origin, we define this. This is definition 1-2 and it's about vectors. A vector is an abstract quantity characterized by the properties. I need to now complete the definition. So here's the full definition. A vector is an abstract quantity characterized by these two properties, magnitude and direction. And that's it. Thus, two vectors are considered equal if they have the same magnitude and the same direction. It looks a bit silly, no? I mean, this is what vector quantities are, but there is a distinction and you need to understand this very carefully. Vector, again I am repeating, okay. A vector quantity, in order to know its value, you have to conduct an experiment and measure its value, which will involve errors and all those things. All those physical things are there which happen in a laboratory or in some kind of test. This is not a physical quantity. It's a mathematical concept which we have abstracted out of those physical vectors. What does it even mean? An example will make it clear. This example will seem very silly from the look of it, but actually it's very important. Say this is an alien, okay, which has accidentally visited us, but for some reason it does not really know anything about counting. It does not know what numbers are. This is highly unlikely. I mean, if an advanced civilization visits us, then obviously they will know the primitive act of counting, but just for the sake of this discussion, say this is an alien and he does not really know how to count. And we present, or say some primitive humans present these three sets of objects to this alien. The first set has these fruits, the second set has these stones, and the third set has these arrows. Alright. Now the alien is observing these sets and it does not really know what counting is, what numbers mean. But still looking at these two sets, it feels that there is something about them that is same, which is not shared by, for example, this set and this set. Right? These things are concrete things, things that we find in the real world. Fruits, stones, arrows, and their collections. There is something about these two sets which, there is a sameness which is not present when one looks at this set and this set, or for example at this set and this set. When one tries to think of it, one comes up with the idea of the size of a set, how large it is, how small it is, and one eventually realizes that there is really no point in discussing about these concrete objects themselves, but it is much more easy and it's more beneficial to create an abstract notion that somehow captures this sameness. And that's how we get the abstract notion of numbers. We invent a symbol that represents that thing which we were struggling to understand, that is same about these two sets. We just simply give that sameness a name, 3, a word, a symbol. We also associate another symbol with this set which is different from this one, which says that sameness is not shared by these two sets or these two sets. Just like that, from the actual physical quantities, which are vector quantities, we have abstracted out the definition of a vector. Does it make sense? Vectors have the same status as numbers have, and vector quantities have the same status as these sizes of these concrete sets of concrete objects have. Now the question is, let's just go ahead with this discussion a little more. Do we really need these things? What is the need for creating these symbols and making our life hell? Well, there are two reasons for it, and both of them are practical reasons. One of those reasons is that we do not want to do the same thing again and again, essentially the same thing. Say someone encounters a set with some objects and another set with some objects, and one then combines these two sets. Say someone goes to the jungle and brings some things, someone else brings these stars, some things, and then they combine the two sets, they put the objects together and get a larger collection. Okay, they have a rough idea of how large this new collection is. Another group does what? Another group brings in some objects like this, some fruits say, and someone from that other group brings 2 arrows, and then they mix those things up and gets a larger set. They observed that if these two sets have that sameness and these two sets have that sameness, and this operation of mixing the sets together is carried out to both the situations, then these two sets also have that sameness. Without trying to understand how large this set is by going through this physical process every time with different sets of different concrete objects, you can write one equation which will tell you what will happen in all such situations. And that equation, of course, is 3 plus 2 equal to 5. 3 is that abstract symbol representing the sameness of these two sets. 2 is the one representing the sameness of these two sets, and 5 is the one representing the sameness of these two sets. So the physical act of bringing the objects together and putting them in one place corresponds to an abstract operation of those symbols themselves. So what do we achieve by doing this instead of doing these things? We save labor and time in trying to know what will happen. Okay, so that is one thing which is practical about developing such symbols and operations on them. But there is one more thing also. So the first need was economy. We do not want to do the same thing, essentially the same thing again and again. So instead we do it in symbolic form and then later translate the result back into the actual thing. But there is a second aim also of developing those symbols, and that is clarity. In a given complex situation, the things that you are interested in may be hidden in a clutter of mess, say these arrows, and somewhere else in a complicated jungle situation you also have these fruits. It is difficult to study the sameness of, in this extremely simple case, it does not really seem like a difficult task to think of these arrows and these fruits and understanding that their sizes are the same, the sizes of the collections. But in a general situation, it may be very complicated, and these unnecessary things distract you. So it's better to just simply think of the symbols which you take out of that complexity, and you only keep what is essential to what you are thinking right now. So to gain clarity also, those symbols help. Now let us go back to our actual thing. So we were defining a vector, and we defined it, and we said that a vector is an abstract quantity having two properties. One of them is magnitude and the other one is direction. And there is a star here. Not that there is a star here. And that star is about something which now we are going to make clear. In order that our set of vectors, not vector quantities, okay, these abstract vectors have a standard algebra, we also include a special vector whose magnitude is 0, and now I have to continue. Okay, so a special vector whose magnitude is 0 and whose direction is not defined. So by the definition that we saw just now of vectors, these abstract vectors, this is not exactly a vector. It's not covered in that definition. But in order to have a standard algebra of vectors, we need this. So we are forcefully including this new abstract, this is also an abstract quantity, into the collection of ordinary vectors, where each one has magnitude and direction. And this of course is called the zero vector and is written like this, 0 with an arrow overhead. And the author cautions that this is not the same thing as the real number 0. Although we are saying that its magnitude is 0 and there is no direction, that may give us the impression that it's just 0. Number 0, no. It's a new quantity which has been made a part of the collection of vectors, where all the vectors have magnitude and direction. This one does not have direction, it has a magnitude, and that is the real number 0. But what do we mean by standard algebra? Well, now let me tell you a little about why this definition of vectors is a very restricted one. This is not the most general definition of the word vector in mathematics. The most general definition is the one-line definition. I mean, if you think of it that way, a vector is any element in a vector space. But we are not going to go into those things right now, okay? There is something in mathematics called a vector space, a structure, something. Any element of a vector space is called a vector. That is the most general definition of a vector. But the kind of vectors that we need for our purposes they are also included in that general definition. Okay, they also form vector spaces, which is in fact what we are calling here standard algebra. Actually, algebra of vectors. But these are specifically, to these vectors which are kind of special, you can attach those two things, those two aspects, magnitude and direction, and that is why they find applications in those places where actual physical vector quantities arise. In fact, that is the source of this notion. Okay, now next we are going to go into the notation for these things. How are we going to write these vectors? Actually, the text uses a different notation than the one I am using. The text uses bold letters to denote vectors, bold uppercase as well as lowercase letters, A, B, C, D, ordinary letters. We, however, cannot conveniently write bold letters here, and you also cannot write it on paper. So that is why instead we use this overhead arrow notation to denote vectors. We can write vectors like this. You can either use lowercase letters, small letters, or uppercase letter, capital letter, but that overhead arrow should be there. And the magnitude of a vector, for example this A, which is a non-negative real number, is denoted by this notation, or sometimes simply by writing the letter itself without any overhead arrow. That also sometimes is used. Okay, so now what? You have started with the definition of a vector quantity, which are physical quantities having magnitude and direction, and then you gave the idea of an abstract vector from them. Just like numbers are abstract concepts representing those operations which involve counting actual physical objects. Alright, and then you also state what notation you are going to use to denote these quantities. But what about the model? What model are you going to use to manipulate these quantities? What is the model, and why is that suddenly coming now? Let's see what the author has said. It is convenient to define operations, because simply having those vectors by themselves is not enough. We also need to have some operations. Just like we have operations of addition and multiplication of numbers, which help us in knowing what will happen to sizes of sets. When sets themselves are somehow combined, or say you break one set up into many parts, then what happens to the sizes of the individual parts? So we need operations. So it is convenient to define operations involving abstract vectors by reference to some simple, easily visualized vector quantity. And you already know that the standard choice is the set of directed line segments. And in this model, each straight line joining two points P and Q, say in that order from P to Q, is a vector quantity where the magnitude is the distance, that is the length of the straight line, and the direction is the direction of Q relative to P, that means in this direction. And it can be any line, not only on the surface of the board, but it can be any line in space. Say you can think of this as a vector where the initial point is this and the terminal point is this, or it can be like this. It can be oriented in any way in space. Okay, so they are vector quantities because each one of the, see again, vector quantities. Okay, so these are actual, concrete, physical or geometric, if you think of them that way, quantities which all of them for their complete specification need magnitude as well as direction, and the magnitude is the length or the distance between these 2 points, and there is a direction from one of the points to the other. Simply mentioning one of them is not enough to specify them fully. We call this the line segment PQ, that directed line segment, and we say that it represents some abstract vector A vector, represents some abstract vector A. Note one thing carefully, that the abstract vectors themselves are not directed line segments. This is only a way of modeling abstract vectors so that we can use this model to define operations on abstract vectors, and we can use this model to manipulate the vectors themselves. And this is not the only way of modeling abstract vectors. There are other ways also, but this is the most natural one, because whenever we talk about magnitude, the magnitude is what? It's ultimately a real number which is either 0 or positive. So that also corresponds to length, and obviously these things have directions because these are geometric objects, directed line segments in space. That is why this is a very natural way of modeling abstract vectors. But as I said just now, there are other ways or other models for abstract vector as well. Another model, for example, is using ordered triples, an ordered triad of 3 numbers, which are some mathematical objects. They also can be used to model vectors. They become helpful in extending the concept of vectors from 3 dimensions to higher dimensions. But we don't need them right now. Right now we are talking about physical vectors, which are quantities which somehow are related to our space. For example, you think of the vector quantities, velocity, acceleration, force, right? We think of them as some kind of quantities which are having magnitudes. We already know what the magnitudes are. Any magnitude is either 0 or some positive real number. But the directions are in 3-dimensional space. So that is why this seems to be the most natural way of modeling abstract vectors, using directed line segments of finite length in space. You should also note this fact that each vector, each abstract vector is represented by infinitely many directed line segments. Say you have some abstract vector which has some magnitude and some direction. The magnitude just happens to be equal to the length of this marker in some unit. and the direction is this, okay, in this direction. Now instead of thinking of this specific directed line segment which is located in space here, precisely here, you can also think of this one. Note that this one and this one are actually two different directed line segments because they are different geometric objects, right? That one is there, this one is here, but as a vector quantity itself, it has the same magnitude as the previous one and the same direction. So like that, there will be infinitely many different directed line segments, all of them having the same length and all of them pointing in the same direction. Any one of them will represent a given abstract vector. So given an abstract vector, there are infinitely many directed line segments in space. Any one of them can be picked and that will represent that vector. So corresponding to each abstract vector, there is a set of these directed line segments in space. Each such set is infinite. Alright. Now let me give you finally, now we are coming to the end of the discussion for this video. It will continue of course. Let me give you an example of two different models of something that we already know, real numbers. Those two models are these. In one model, a real number is a formal limit of a Cauchy sequence of rational numbers. There is no need to understand what this thing means. In another model, a real number is a Dedekind cut. These are two entirely different things. A formal limit of a Cauchy sequence of rational numbers is one thing and a Dedekind cut is something else. A Dedekind cut is a special type of subset of the set of rational numbers. If one develops real numbers like this, one gets one theory and this leads to another theory where the objects are different but the theories become identical. So it does not really matter whether you choose this one as a model for real numbers or this one as a model for real numbers. Just like that, you can use directed line segments as a geometric model for the vectors that we have defined here, which ultimately themselves capture the idea of vector quantities, or whether you use ordered triples of real numbers as another model for vectors, you ultimately are going to get the same theory for vectors, essentially the same theory. So let me end this video here itself. In the next video, we are going to define operations on vectors. The well-known operations of addition of two vectors, multiplication of a vector by a scalar, these things. If you recall, before I end, if you recall that small example where we showed that when we bring two collections of objects together, mix them up, then we get a large collection, that corresponds to the operation of addition of numbers. Just like that, when you take two concrete vector quantities, say you take two velocities or two forces, you can add them, which has a definite meaning for velocities and a definite meaning for forces. Okay. And mathematicians and physicists studied these things and then they came up with the most suitable definition for addition of two abstract vectors, which somehow captures all these concrete additions simultaneously. So we will see those things.